Hello and welcome to our demo for the project Integrating Evolutionary and Geometrical Optimization Methods with GIS for Sensor Placement. So what is the goal in our project? Assume that you have a number of sensors and a field to cover. Where will you put the sensors to maximize the coverage? You can put them randomly as shown in the bottom figure, but as you see in the top figure, the coverage might not be very good. Another approach which makes more sense is to place them based on a grid. But as you see here, the coverage could be better. So what is the problem? It is the topography in rural areas and the buildings in the cities which affect the coverage of the sensors. In other words, GIS is the missing piece of the puzzle for a realistic coverage estimation of sensors. In this project, we have implemented a number of optimization methods to maximize the coverage of a sensor network considering the topography of the environment. The first method is simulated annealing, which is a simple stochastic optimization method. In each iteration of this method, the position and orientation of one sensor is changed slightly, and the new coverage is calculated. The new position is accepted if the coverage has been improved or a random value is below a predefined temperature function. Here, the progress of the algorithm is shown in high speed. Next optimization method is covariance matrix adaptation evolution strategy, or cma-es. This method tries to learn a second-order model of the objective function by sampling several points in the search space and evaluating their performance. As you can see here, in the first iterations, the position of sensors is changed largely, and as the algorithm proceeds, it gets more stable until it converges to the final solution. The last algorithm which we are considering is the classical gradient descent method. In each iteration of this algorithm, the gradient of the objective function is calculated analytically, and then the position and orientation of sensors is changed to maximize the coverage. The main benefit of this algorithm is its low computational demand, meaning that it needs between 10 to 200 times less computation compared to the last two mentioned methods. The other benefit of this algorithm is that it's distributed in nature, meaning that each sensor only needs to know its own position and the position of its neighbors to move inside the environment. It also scales very well for large problems. For the experiments, we ran our algorithm on the map of a rural area in North Carolina and the map of Laval University campus. We performed experiments on different map sizes to see how each algorithm scales for different map sizes. As you can see here, the gradient descent method outperformed the other methods in terms of coverage in most of the maps. Especially as the size of the map increases, the difference between the performance of gradient descent and other methods become more clear. It also has a smaller processing time, which makes this a suitable method for optimization of placement after deployment. For the future stage of this project, we will be working on hyper-heuristic optimization methods to extract heuristics on how to move sensors to improve the overall coverage. On the other hand, we will also work on the multi-objective optimization to maximize the coverage and minimize the number of sensors at the same time.
The geometric approach is based on Voronoi diagram. Each Voronoi cell shows the region which is supposed to be covered by its internal sensor. The difference between sensor sensing range and the Voronoi cells defines uncovered area. Our mobile strategy pushes sensors toward the farthest Voronoi vertices. In these movements, new positions will be found and the coverage is supposed to improve after each iteration. As mentioned in the optimization part, we have integrated special information in our algorithm. For movement step, each sensor stops at the highest elevation of the connecting line between sensor position and its farthest Voronoi vertex. Integrating 3D city models helped us to accurately consider obstacles and city objects and apply the algorithm in an area with higher level of detail. In this short movie, the implementation of the geometric optimization approach is presented. Here is the 3D fly-through of the obtained results of the study area. Green area are the covered regions, and violet are uncovered. The results for two urban and rural area has been presented here. Improvement in both visibility and coverage of two areas can be seen. As the next part of our investigation of geometric approach, we've studied on the impact of spatial data quality on coverage estimation. From different elements of spatial data quality, positional accuracy and completeness were chosen. In terms of positional accuracy and intentional error, and the coordinates of buildings' corners were applied. As the second quality element, completeness was investigated. Some buildings were deleted and optimization algorithm was executed. Here, you can see the impact of positional accuracy and the completeness. The results of data quality assessment are represented here. The error matrices show these impacts. In terms of future stage, we will be working on improve the ability of our algorithm to add and remove sensors in addition to just move them. Our other goal is to test other levels of positional accuracy and work on maps with higher LODs.
Finally, I would like to thank you all for attending our demo. I would also like to thank all the people who participated and collaborated in this project. Especially, I would like to thank GEOIDE for providing the funding and giving us the opportunity to make this project happen.